Today we're going to go through some best practices on how to protect your device under test from being damaged during a test sequence. I'm Brian Whitaker, a product marketing engineer here at Keysight.
And I'm Daniel Bogdanoff, a test geek here at Keysight. And Brian, I'm excited to not blow up some things today. So why don't we get started?
Let's do that.
So what causes a device under test to break when you're using a power supply with it?
So too much power, either too much current or too much voltage. And we can put protections in for both. Overcurrent protection and overvoltage protection will automatically shut down the output if the condition you set occurs. Now let's see overvoltage protection in action. Let's grab the thermostat DUT.
All right.
And plug it into channel 2. So this is the high performance power supply, although we could really run this test on any of the supplies.
Yeah, 100 watts might be overkill for an IoT.
Probably. You can run on any of them. For this demo, let me go ahead and just use the front panel.
Okay.
Sound good?
Yeah, set her up.
Okay. Now, let me go to the main menu, go to Protect, Overvoltage Protection, and let me set it to 3.2 volts. So now we're ready to run the sequence.
So we have overvoltage protection at 3.2 volts. Right now, when you turn it on, it's going to go to 3 volts, and then you're going to spike it up over the limit.
Yep.
Okay.
That's right.
Let's see it.
Let's see it. Okay. We run the sequence. We'll turn on. Now it'll be a 2-second delay. And then we went to 3.3 volts, and you can now see that it's shut down.
The screen is off.
Yep.
So overvoltage protection, it worked. Overcurrent protection is essentially the same thing. But is there like a expert mode protection mechanism?
Yes, absolutely. So the N6700 also supports smart triggering. Example of this is delayed overcurrent protection. You can set a lag for when the output shuts down for applications where a current spike is part of the regular operation.
So maybe the device can handle a quick spike in current, but it can't handle sustained high current.
Yes, correct. So that is where that smart trigger is very important. And we can actually show that using the DC to DC converter, or DUT.
Okay, I'll grab that. You set up the script.
Okay, sounds good. So here you can see we have the DC to DC converter connected to the instrument, both the power supply and the electronic load. And I've developed this script to really showcase the OCP protection of the box. So the way the script is set up right now is that the overcurrent protection is set at 0.6 amps. But I've set a delay of 250 milliseconds.
Okay, so it should be okay to go overcurrent as long as it's less than that 250, 225 millisecond window.
Right.
But if it stayed high longer than that, it would trip.
Right. So the way the script is set up right now is that it will only go over that limit for 225 milliseconds. So the hypothesis is that the DC-DC converter will still be functioning after the script runs.
Okay, so let's hit run.
Right.
And then for a moment, the current goes too high, and it would normally trigger overcurrent protection, but it's such a small pulse. With delayed overcurrent protection, it's not going to trigger it. So when we make a measurement, we should see...
You should see this. So here you can see where the current level went above the limit, but it didn't go above the limit for longer than 250 milliseconds. So here you can see it actually did not trip over current protection. So the DC to DC converter is still functioning.
Okay, let's try a script, and I think you have one where it stays high for too long,
right?
And then it should shut everything off.
Right. So all I have to do is change this wait period to 275 milliseconds. And update this step and hit run.
So same thing.
The
current spiking over our limit. I heard another relay click, so I assume it turned off.
Yep.
When we look at the results.
Here you can see, yep, it shut off.
Okay.
So it's virtually zero current.
If your device is tolerant to small spikes, something like a delayed overcurrent protection would be a perfect, expert mode mechanism.
So yeah, it's perfect for devices like that, where it briefly has to go above the overcurrent protection level, but you still want the device to continue to function. So another basic feature is over temperature. So just in case the box gets too hot, it'll automatically shut down if it reaches a certain temperature level.
So we have overcurrent, overvoltage, temperature. What else do we have?
So another feature worth highlighting is the watchdog timer. This feature provides protection when the test program freezes or the controller stops communicating. The output watchdog timer causes all outputs to go into protection mode if there's no skippy I/O activity on the remote interfaces within the user specified period.
So basically, if you are quiet for too long, it shuts everything down.
Yes, absolutely.
Okay.
You can set this feature using skipping commands or from the front panel. So let me go to the front panel and show you how to set up the command. So let me go to the main menu, then go to Protect, Watchdog, And here you can enable watchdog as well as set to delay.
So we've done overvoltage, overcurrent, delayed, temperature, watchdog.
Yep.
I'm out of fingers on my right hand. Do you have a
Oh,
sixth?
there's more. There's more. An additional way to protect your device is set the slew rate to reduce inrush current. Variable slew rate controls adjust how fast a power supply can change one voltage level to the next. Slowing the rate of voltage change reduces the rate that current flows into the capacitive device. Many devices have an input capacitor to help regulate voltage. Also, some devices have unattended capacitance based on their design or wiring. For example, an incandescent automotive taillight has a high capacitance. As a result, it generates an inrush current that consistently burns out fuses. So you can see in this first figure that the inrush current of 8 amps is 4 times larger than the steady state current. An 8 amp inrush current occurs at 12 volts. However, if we set the slew rate to 10 volts per second, a peak current is negligible as shown in the following figure. You can figure the slew rate on the front panel or through skipping.
That makes sense. So if there's high capacitance, a step function is going to send a bunch of current through. But if you slow that down, it kind of charges up the capacitance and is a much more friendly way of switching voltage levels.
Smooths it out.
Okay, what else do you have for me?
Another cool feature is list mode.
I can guess what list mode is, but why don't you explain it for me?
Sure, so list mode can be used to protect your device against overpower. A single overvoltage or overcurrent protection level works well for protecting a device that has a single maximum voltage and current. However, some devices' max current changes with voltage. A good example is a DC to DC converter. Every DC to DC converter has a max power rating. An increase in voltage will cause the max current to decrease. For example, this 12 volt to 6 volt 3 amp converter can handle an 8 volt to 18 volt input. A power supply can test the input from 8 volts to 18 volts, but the max current limit needs to be set independently for each voltage step. A current acceptable with an 8 volt input would be damaging at 17 volts, so the current limit needs to vary with the input voltage. So I've created the Skippy sequence in Command Expert to step through a voltage and current limit sequence for the DC to DC converter. So here is a Skippy sequence that I've created. So here you can see it creates a list with these voltage levels, but also with these current limit levels. Plus it sets a dwell time for each of 5 seconds. All right, so once I hit run, it'll run through that sequence.
Let's do it.
Okay.
So we should be seeing the power supply ramp up its input voltage into our DC to DC converter. And for each voltage level is a separate current limit that basically drops down as the voltage goes up.
That's right.
So our power limit is kind of the same.
Right, right. It's all automated with this Skippy sequence.
Okay.
You can also do it on the front panel, though, as well.
So I feel very protected in 6 or maybe even 7 ways if you include list mode. What should people do next?
So I highly recommend checking out our other videos that go through how to program the N6700C, how to set up the power supply in a rack mount, and also how to select the right modules for your application. Thank you for watching.